Okay, so this is the last PowerPoint of this section, and there'll be a worksheet that'll be relating to all these. And so let's finish it up. So the last two models relate to what we're interested in, how a atom behaves. The orbital energy diagram gave us all the information we need to know. Okay, the energy level, subshell, orbital, electrons, and spin. Electronic configuration model lost the orbital and the spin, and only left us with the energy levels of subshells and how many electrons are in each subshell. Both of them gave us a valence shell and a number of electrons. Okay, that's great, because that's exactly what we're looking at. But what we want to do is have something that'll actually, now we know what the structure of the atoms are, but what we want to do is actually see how that might relate to how it behaves. And so what we're going to do is come up with models that tell us something about its function. So I call these functional models. And there's the Bohr model. And if you look at Bohr model in your book, it's not, so I should actually put this in quotation marks because it's not the Bohr model you see in books with dots all over the place. This is my version of the Bohr model, and there's something called Lewis dot. And what these are going to do is help us determine the function of atoms based on their structures. So I call them functional models. The Bohr model is going to help us understand why some atoms are better at being reduced and other atoms are being oxidized. And also why sodium has a plus charge, fluorine has a minus charge, and so forth when they're ions. Lewis dot model will help us with when we talk about molecules and how we can get these bonding structures of covalent molecules, like water. What is the structure of water? Now, you know it's two hydrogen, two oxygen, but how do they connect to each other? And that's what we're going to use, Lewis dot structures. And we'll be using them after we're all done with this section, which we still got more to cover. So this test is just going to do with the electronic structure of an atom. And then what we're going to do is apply that. The next test after that, hopefully if we get to it, it will talk about the Bohr model simply is this. It tells basically how big an atom is. And how big an atom is determined by how many energy level it has. The more energy levels you have, the bigger the atom. It's also going to include the valence electrons. All right, and what we're also going to do is that we're often going to the valence shell, if there's electrons missing from it, we will incorporate them as well. So let's start out with oxygen. And what we're going to do is use the periodic table to figure out the Bohr model. We can use the orbital energy diagram, and we can go back and look at PowerPoint 1. We went over the orbital energy diagram of oxygen, and we found that it has electrons in 1s2, 2s2, and 2p. Okay, 2p4, and so we knew that it had two shells and it had 6 valence electrons. And then we could do the same thing with electronic configuration. But what we just went over at the end of the last PowerPoint is you can figure out the energy level by what row it's in and how many valence electron it is by what column it's in. So oxygen is in row 2. So it has 2 shells. It has 6 valence electrons, and you can figure out that because it's in column 16. And each hash mark represents an electron. And it doesn't matter how you do these. You can put them all together. You could just randomly put them all over the place, or put them all together. And for nonmetals, what we're going to do is include where there's not electrons in the valence shell. So there's a total of 8 possible spots in the valence shell. 2 from the S's and 6 from the P's. And so there's 2 empty spots. So this is the Bohr model, and we'll see how this will help us figure out the how well an atom is oxidized and reduced when you get to the next section. All right, here's the Bohr model of calcium. All right, quickly, we don't have to do the orbital energy diagram or electronic configuration. We can just figure it out from periodic table. It's in the 4th row, so its valence shell is 4, so it has 4 levels, 1, 2, 3, 4. It has 2 valence electrons. It's in column 2, so 2. There you go. It's that simple. All right, Lewis dot structure. What we're going to do is we're going to look at just the valence electrons and how they're arranged in the atom. So that's going to be key, is look at the arrangement. What we found out at the end of the last PowerPoint, the total number of valence electrons could be never more than 8. So what we're going to see is that there's only 8 different Lewis dot structures for no matter what atom. That's because the Lewis dot structures will be redundant. For instance, all the elements in column 1 will have the same Lewis dot structure. All the columns and elements in column 2 will have the same, and so forth. Okay, the key to the Lewis dot structures is how the electrons, represented dots, are placed on the model. For the Bohr model, it didn't matter how you put the valence electrons. I just put hashes on the valence shell. For Lewis dot structure, in the long run, we're just going to worry about column 1, 14, 15, 16, 17, 18, because these are the nonmetals. And we use the Lewis dot structure for figuring out covalent molecules. Remember, covalent molecules are made out of nonmetals. Okay, so let's get to it. All right, the method. So start out with carbon, and we know that carbon has 4 valence electrons, and we can quickly determine this because it's in column 14. So what you do is you put a square around the carbon, the symbol. Okay, then what you have to do is you have to put 4 dots, each dot representing the electron. Now, what we want to do is go back to doing the orbital energy diagrams and doing the P's. When we did a P subshell. When we did a P subshell, there was 3 orbitals. And what you did is you went up, up, up before you paired them. You didn't go up, down, up, down, up, down. You went up, 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 then down, down, down. So each square got an arrow before you paired them up. So we're going to do a kind of same thing here. You're going to put a dot on each side before you pair them up. So carbon has 4 dots. So what you're going to do is put a dot, 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 dot. And it really doesn't matter where you start. You go dot, 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 dot. You just can't pair them up. And you can only put 2 dots on a side, no more than 2. Just like we talked about, or each orbital. You only put 2 arrows. Okay. So carbon is dot, 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 dot. And then what we're going to do is, because there's 4 empty spots, you're going to put the empty spots on as well. And there you go. So that's the Lewis dot structure of carbon. All right, for oxygen, oxygen has 6 valence electrons. You can figure that out. It's in column 16. It's in row 2. We don't care about that. All we care about is how many valence electrons it has. So it goes. So the first go 1, 2, 3, 4, and then the 5th and 6th go on any side. I just put them on this side, and so now I have 2 pairs and I have 2 unpaired. Okay, often what we do is we leave the square off and just leave the dots. And then hydrogen. Hydrogen's a little different because it doesn't require a square, because it's in the first energy level, and the first energy level you can only put 2 electrons. Energy level 2 and further up you can put 8 electrons in the S and P's. So hydrogen, you don't have to use a box, you just use a line. and it has one electron, so it has a dot, and it has an empty spot, so you have an open spot. Okay, and so these are the Lewis dot structures for the main elements that we've talked about. Here's carbon, and here's oxygen. Nitrogen has 5 valence electrons. This 7 is not how many valence electrons. That's how many total electrons it has total. So it had 5 valence electrons because it's in the 15. So 14, 15, 16, 17. So it has 1, 2, 3, 4, and the 5th dot you can put on, I just put it over here. Here's oxygen, here's fluorine. It has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And if you notice, all the elements in a column will have the same Lewis dot structure. So silicon looks the same as carbon, phosphorus, nitrogen, and so forth.